In this video, we'll discuss a few, right? Three more indeterminate forms, which are in the exponent form. So you have f of x to the power g of x as x goes to a, right? A fixed a might be infinity, negative infinity, a plus, a minus, left side, right side, or a. And which three are indeterminate forms, right? First one here is you have type 0 over 0. What's the meaning of that is if you have f of x goes to 0 and g of x also goes 0 as x goes to a. Or type infinity to 0 if f of x goes to infinity and g of x goes 0 as x goes to a. Or the type 1 to infinity if the base f of x goes to 1 and g of x goes to infinity as x goes to a here. So this is the three types of indeterminate form, exponent form, right? So again here, we have only one technique, which is L'Hopital's rule to use. So all we can do is change from exponent form to a quotient, then apply L'Hopital's rule, right? So that's our only strategy. So let's see two examples. And the first one here is as x goes to a here. No, not a. It's a fixed number. Fixed number is 0 plus. Goes to 0 on the right side. You get 1 plus sine of x to the power cotangent of x, right? Okay, now you can see that as x goes to 0 on the right side, 1 plus sine of x goes to 1 on the right side, and the cotangent of x goes to pole to infinity, right? By the definition of cotangent cosine over sine, right? Which is 1 over 0 plus. So this is 1 to infinity for sure, right? How do we handle 1 to infinity? We need to change this to a quotient. How do you change this to a quotient? You want to bring the exponent down. How do we bring this exponent down here, right? We have only one trick, is taking natural logarithmic function, right? So we give a new name for this function. Let h of x equal to 1 plus sine of x times to the power cotangent of x. We take a natural log. Natural log of h of x is cotangent of x times natural log of 1 plus sine of x. Now it's easy to write this as a quotient because cotangent is cosine over sine. You get cosine of x times natural log of 1 plus sine of x over sine of x, right? Now you can see that as x goes to 0, the numerator here, 0 plus cosine of x times natural log of 1 plus sine of x. This one goes to 1 times 0, which is 0. Sine of x also goes 0, so this is 0 over 0, right? So this one is easy to evaluate. Let's try to do that. So we know that as x goes to 0 plus natural log of h of x equal to as x goes 0 plus cosine of x times natural log of 1 plus sine of x over over what? Over sine of x. So this is 0 over 0 by our discussion. So this is as x goes 0 on the right side, you get negative sine of x times natural log of 1 plus sine of x, and plus cosine of x times 1 over 1 plus sine of x times cosine of x over cosine of x. Now, if you plug in 1, you can see that the first term here goes to 0 because sine of 0 is 0, right? Second term here goes to 1, right? And cosine of 0 is 1. So this limit is 1. So the limit of natural log of h of x is what? Is 1. So we know that as x goes 0, h of x, which is a function we are starting from. So this is same as x goes 0, e to the power natural log of h of x. Change the function form a bit, right? E to natural log cancel each other. This function is continuous. So this is same as e to the power as x goes to 0 plus natural log of h of x. We know this limit goes to 1, so this is e to 1. So the answer is e, right? So basically, after you figure out the limit of the function with natural log, you can go back to the original function, right, to figure out what's the limit. Now let's see one more example. Let's see one more example. B here. What's the limit as x goes 0? No, infinity. X to natural log of 2 over 1 plus natural log of x, right? So that's a exponent, indeterminate exponent. Now let's see what's the type of that. So you can see that as x goes to infinity, the base is for sure infinity, right? Now what's the exponent? Natural log of 2 over 1 plus natural log of x. So natural log of x will go to infinity. So this is a finite number over infinity. This one goes to 0, right? Any finite number, no matter you have 1 billion, 2 trillion, so that's over infinity, right? It still goes 0. So this is infinity to 0. Again, here, very complicated exponent, right? So we want to somehow change it to a quotient. How do we do that? Introduce a new name, which is h of x. So this is equal to x to natural log of x 2 over 1 plus natural log of x. So take a natural log, h of x. We don't have a natural quotient, just do that. So this is natural log of 2, bring down the exponent times natural log of x, right? So this is natural log of 2 times natural log of x over 1 plus natural log of x. So as x goes to infinity, so the numerator here for sure goes to infinity, denominator also goes to infinity because this one goes to infinity, plus 1 or time a positive number always goes to infinity, right? So we know that we get a infinity over infinity kind of limit. We can apply L'Hopital's rule, right? As x goes to infinity. So this is a natural log of 2 natural log of x over 1 plus natural log of x. This is infinity over infinity. We can differentiate. This is as x goes to infinity, natural log of 2 times 1x over 1 derivative 0 and plus 1x, right? So 1x, they cancel each other because 0, really, they don't have anything, right? So this is natural log of 2. Now we are ready to evaluate the limit of the original function x goes to infinity. Original function is h of x. Right? By our algebra, this is same as x goes to infinity e to natural log of h of x, because natural log exponential function, they cancel each other. So this is equal to, because the function e exponential function is continuous everywhere, so you can put the limit in the exponent position. And this thing here we happen to know. So this is e to natural log of 2. So this is 2. So our final answer for this problem is 2, right? So all we need to do is just change our exponential function to a quotient by taking a natural log both sides. If you know the limit of this quotient, just raise back to the original function, you get the limit of the original function. So that's how do we evaluate this limit.